Okay, so hi and good day everybody. Welcome again to Principles of Reinforced Concrete Design. And in this video lecture, we would be discussing about the analysis of singly reinforced beam in USD. So from the previous video, we have discussed there the design philosophy of USD. And the basic idea in designing is that the design strength, or let's say the strength of your structural member, should be greater than or equal to the required strength. And your required strength is to be the stress as brought about by your external loads. And also in the previous video lecture that we had, in the previous meeting, we have discussed on how we would be solving for the required strength without using any of the structural theory matters, such as your moment distribution method, your slope deflection method, and etc. So once again, from the previous video lecture, we have discussed there on how we would be solving the required strength using the simplified approach or the simplified method as per NSCP. So there. So once again, guys, the required strength is basically your MU. And your MU can be solved using, once again, the simplified method and, multiplied by the load factor. So this can be, let's say, 1.4 dead load, or let's say 1.2 dead load plus 1.6 live load, and etc. So all of these load combinations are in the National Structural Code of the Philippines. So anyway, that is for the required strength, I should say. So how about for the design strength? So your design strength, so once again, your required strength should be less than or equal to your design strength. So your design strength is to be the strength of your member, so that is to be the nominal strength, multiplying it by the reduction factor phi. So this is basically our factor of safety. So once again, PMN should be PMN should be greater than or equal to your MU, or that is to be your required strength. And for your phi, guys, so for the value of your phi, it can be seen here in this table. So that is to be in page 4-140 of your NSCP 2015 edition. Okay, so anyway, so for example that you are to design it, you are to analyze it in moments. So let's say that it is to be a flexural member. The value of your phi will depend upon which case it would be. So it would be from 0.65 up until 0.9. On how we would be choosing 0.65 and 0.9, I will be explaining that to you in the videos to follow. Anyway, so if you are to have a structural element of a shear element, your reduction factor phi is to be 0.75 and etc. So there. So that is for your value for phi. And for your value of Mn, so this is to be the nominal strength of your member. And since this is to be letter M, as you can see, so letter M signifies moment. So when we say Mn, this is to be the maximum moment that your structural member can carry. So when you say Vn, this is to be the maximum shear that your structural member can carry. That is to be the idea of this principle. So for example, guys, that we would be having a certain structural member, let's say a simply supported beam. So I will just be drawing a beam here. So let's say that this is to be your beam. And once again, let us assume that this is to be a simply supported one. So we have a pin here or a hinge, and we also have a roller here. So if we are to subject this member with with transverse load, so let's say that these are to be your transverse loads. So let's say that it is to be a uniformly distributed load. The tendency of this structural member is to bend in this particular manner. So by deflection, this is to be its moment of bending. So if we are to draw its moment diagram, so let's say that this is to be its moment diagram, it would look like this. So this is to be its moment diagram. So as you can see, guys, that in this moment diagram, we can say that the most critical part is to be the midspan. So by the way, guys, this is not drawn into scale. So apologies for my weakness in drawing, but well, you get the point. So there, once again, that this is to be the maximum moment. So if this is to be your maximum moment, it means that the section here at this portion right here is to be the most critical one. So it is to be here. So this is to be the most critical one. And If you can remember, guys, from your mechanics of deformable bodies or your strength of materials, that if this is to be your manner of bending, it means that the fibers at the top portion, so the fibers at the top, will now be subjected with compression, and the fibers at the bottom will now be experiencing tension. Okay, and if that is to be the case, so I will just be redrawing it for it to be much more presentable. So once again, let's assume that this is to be the manner of bending. Oops, sorry. Say that this is to be the manner of bending. So just for pretend. So we can safely say that the fibers at the bottom part will be subjected with tension and the fibers at the top part will be subjected with compression. And with that, if you can remember from the previous video lecture, we can say that plain concrete is very weak in tension. So once again, it is to be strong in compression, but it is to be relatively weak in tension. And for us to address that issue, as engineers, what we would be doing is that we would be placing reinforcing steel bars here so that we would be having an adequate tensile strength. So with that, guys, so for example, that the red ink is to be your rebars, so we will now be placing it at the bottom part for it to resist tension. So that is basically the idea on your reinforced beams. Okay, so if for example that we will be getting this particular section, so let's say that we will be cutting this. So we will be getting this section right here. It would now look like this. Whereas the top portion of your concrete does not necessarily need a rebar, and this one at the bottom is to be your reinforcing steel bar. So once again, this is to be a rectangular section of a reinforced concrete beam. Okay, so once again, guys, the bottom section, the bottom part is to be subjected with tension and the upper part will be subjected with compression. So if we are to draw its strain diagram, so by the way, wait. So let us now draw its strain diagram. So let's say that this is to be it. And this, I'm sorry, I think it's better if I would be drawing it here. So once again, the upper portion will now be subjected with compressive strain. So once again, this is just to be the strain diagram. And according to NSCP, the strain for your concrete should be equal to 0.003. So by the way, take note of that. And once again, that the strain, as it approaches your neutral axis, will now decrease. So let's say that this is to be the neutral axis, so it will be decreasing here. And after this, so going further, it would now experience tensile stress. So it would be like this. So this is to be its basic stress strain diagram. So if this is to be your tensile strain, its stress diagram would now look like this. So let's say that this is to be its stress diagram. So the stress here, so by actuality, it would now look like this. So I will just be drawing it red. So it would now look like this. Approximately, by the way. So anyway, so that this is to be the strain, the stress of your concrete. So this is to be the stress of your concrete once again. And once again, since your concrete does not have any capability to withstand tensile stress, so that is according to the USD, so that is to be our assumption, we would not be having this particular stress right here. So we would just be removing this. But since we have our rebars at this part, the rebars will now be the one that will resist tensile stresses. So this is now to be it. So let's say that this is to be for your tension. So tension, and this is to be a distributed load. This should be a pressure. But as you can see, guys, if this is to be your strain diagram, your stress diagram, it would be very hard if we would be solving for its resultant because we do not know how to solve for this area. So according to Whitney, so I'm not quite sure if he is a person or if she is a person. But anyway, so a Whitney's diagram would now be looking like this. So this is basically its approximate area in rectangle. So by the way, so once again, since we cannot solve for this area, researchers before has found out that the approximate uniform stress that is equivalent to this area would now look like this. Okay. Whereas if this is to be FC prime, for example, or F prime C, so it will be up to you if you would be calling it FC prime of or F prime C. So let's say let's say FC prime, where FC prime is to be the strength of your concrete. So FC prime is to be the strength of your concrete. So if that is to be FC prime, this area right here, which is to be equivalent to this, or approximately equivalent, is to be 0.85 FC prime. However, if this is, so let's say that this is to be your value for C. So just for pretend once again, so let's say that this is to be for the value for your C. This dimension right here, so this dimension right here is now to be equal to A. And A is equal to betas of 1 C. So given C, we would now be solving for A using betas of 1 C. So there, and once again guys, this area this area will now be equivalent to this particular area. So this is much more simplified. And if you can see, solving for the resultant here would be much more easier than solving for this resistant. So let's not forget the tension stress here at the bottom part. So this is now to be its tensile stress, T. Okay, so basically guys, for us to solve for the value of our Mn, so once again, for us to solve for the value of our Mn, or the nominal flexural strength of this particular member, what we will be doing is that we will be getting the moment about any point at your beam. May you be getting the moment here, or getting the moment here, or getting the moment here. So it doesn't matter as long as you would be getting the moment about any point. Since this is to be at a static equilibrium condition, you would still be arriving at a certain answer. So let's say that the resultant here, the compressive resultant here is to be at this point. And let's say that this is to be for the value for your C. So there, and let's say that the location here, so let's say that this is, this dimension is to be A over 2. So by the way, I will just be redrawing it. So let's say that this dimension is to be A over 2, since this is to be the value for A, and for the resultant of a rectangular pressure is to be at its midspan. So this is now to be A over 2. And let's say that this dimension, so from the topmost fiber of your beam or the compression fiber up until the centroid of your steel, so let's say that that is to be D. So let's say that that is to be for your value D, or the depth. So meaning that guys, this particular dimension is to be D minus A over 2. So once again guys, from the topmost fiber up until the centroid of your steel, that is to be D. And if you would be subtracting this much, this is now to be A over 2. So from this point up until the centroid of your steel, that is to be D minus A over 2. So with such guys, for you to solve for the nominal strength Mn, you can either get the moment about this point, or the tensile stress. So let's say if you would be getting the moment here, so we have C, or the compression stress C, times the lever arm. And our lever arm is to be D minus A over 2. So D minus A over 2. So once solving this, then you're already done. And another equation is that, for example, that we will be getting the moment about this point. So let's say that we would be getting the moment about the center, the resultant of your pressure, that is now to be equal to tension, so T, So this is now to be the force times the lever arm, and that is also equal to D minus A over 2. So basically, guys, this is to be the equation for our nominal strength. But what is to be the value for your C? Okay, so the value for your C is to be the resultant of the pressure. So this is to be the pressure and the area. So basically that is to be the volume. Because if we would be drawing our beam in 3 dimensions, so let's say that we will be drawing it here. So let's say that this is to be the beam. So this is just for example. So let's say that this is to be your beam. So let's say that this is to be a hidden line. Okay, so anyway, so suppose that this is to be your beam. And by the way, guys, this, pressure diagram right here, or the stress diagram, is to be 3 dimensions. It is just that we are looking at it at the side view. Thus, it would look like this. But if we would be looking at it in a 3 dimensional view, so for example, that this is to be the value for your A. So let's say that this is to be your dimension A. And by the way, guys, this is to be your BW. So by the way, this is to be BW, which is to be the base of the section. Anyway, so let's say that this is to be BW and this is to be the A, which is to be this. So this is to be for your dimension A. And well, with that, guys, this is now to be the area. And this is now to be its stress. So it would be this, 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 and this. So this is now to be a pressure. So once again, it is not to be this portion right here is not to be a uniformly distributed line load. Rather, it is a pressure. So it would be looking like that approximately. So apologies once again for my rather mediocre drawing. So, and if you can remember that the strength of your concrete, which is Fc prime, this is now to be in terms of megapascal. So megapascal. And megapascal can be rewritten as newtons per millimeter squared. So with such, guys, if we would be multiplying this by an area, so let's say Fc prime times area, for example, this would now yield at a unit of, so newtons per millimeter squared times, so what is to be the area here? So BW times A, that is to be millimeters, times millimeters. So millimeters would cancel out, which would leave you at an answer of newtons. So this is to be basically the value for your C. So once again, that is to be 0.85. Oh, by the way, guys, this is to be 0.85 as per this equation. So this is from Whitney's stress diagram. So 0.85 Fc prime times A times BW. So once again, for us to solve for this, for the compressive load or the resultant of the compression force, so it would be directed at the middle part. So let's say that that is to be the middle part, which is approximately here. So this is now to be equal to, so 0.85 Fc prime, because that is to be the magnitude of the stress. So that is to be 0.85 Fc prime times A times BW. So this is to be for your value C, compression. So I will just be writing them here. So C. So this is now to be equal to 0.85 Fc prime A BW times, of course, this one. So times D minus A over 2. And for your tension, so for your tension, that is basically the area or the total area of your rebars. So let's say that that is to be AS for pretend. So AS, so area of steel. So once again, that is to be the total area of the steel times the stress of the steel, Fs. So basically, that is to be for your value of T. So this is now to be AS, Fs. And as for your C, I will just be writing them here. So apologies for the lack of presentation. So C This is now to be 0.f85. Nah, I think I will just be writing them at the top. So 0.85 FC prime AB. So that is basically stress times area. So there, and if you would be getting for the moment, so this is now to be equal to ASFS times D minus A over 2. Okay, so once again, guys, as you can see here, FC prime is to be the strength of your concrete. So in this case, guys, for example, that your FC prime is to be 28. Then basically that is to be 28 megapascal. So once again, FC prime is to be the strength of your concrete. But what about for FS? So if you would be asking me, isn't it FS, isn't FS the strength of the steel? Or isn't FS equal to the yield stress of steel Fy? So the short answer to that is, well, no, not really. Not always. Okay, so there. So as you can see, guys, we already have this particular equation. So we have 0.85 FC prime APW and ASFS times D minus A over 2. And from this equation, guys, so I will just be rewriting it at a new page so that it would be much more presentable. So there. So this is to be MN, or this. So they should yield the same answer, guys. So there. But we have a problem here. So in your analysis part, these are to be the given parameters. So for the given parameters, these are to be it. So AS. So you can solve for it by just multiplying the area of one rebar and multiplying it by the number of rebar. So this is to be given already. And how about for your FC prime? This is already given. So this is already predetermined. And what else? So we also have BW. So we already have this BW. That is basically the width of your beam. And we are also given your depth D. So with such, we already have BW and we already have D. But what about for A? So we do not know the value of A and we do not know the value of Fs. So once again, your Fy is already predetermined. So you can already know the Fy. But we do not know if Fy is to be equal to Fs. So if that is to be the value that we will be using here. Okay, so for your A, guys, so for the value of A, this is basically equal to betas of 1 times C. So for your betas of 1, it can be given by this table. So for example, that your FC prime is to be from 17 up until 28, your betas of 1 would now be simply 0.85. But for example, that your FC prime is greater than 28 and it is to be less than 55, it is to be given by this equation. But take note, guys, that if you would be opening the first printing of your NSCPs, the equation would be 0.85 times this value. But this is rather erroneous, guys. So there should be a minus sign here. So basically, the correct equation here, so this is erroneous. So the correct equation here is to be 0.85 minus 0.05 times F prime C or FC prime minus 28 divided by 7. So once again, do not use this. So I'm not quite sure if in the second printing this is already corrected. But once again, this is to be the correct equation. Okay. So going back, so we already have the value for our betas of 1. But what about for the value for your C? So for the value for your C, guys, we can actually solve for it using this diagram. So I will just be copying this diagram. So let's say that this is to be the diagram. And if you can remember, guys, this dimension is to be D. So this is to be D, or the depth, or the effective depth D. So once again, that is to be this. So this D. And there. And I have also indicated earlier that from the code, that the maximum, the strain of the concrete should be equal to 0.003. So for us to determine this, so for us to determine the value for RC, we can solve for it using basic trigonometry or basic geometry, or we would just be making use of ratio and proportion. So with that, guys, I will just be getting this ratio here. So this triangle, and I will be comparing it with this big triangle here. So this triangle. So I will be comparing both of them. So for the smaller triangle, so that is to be C divided by, so C divided by 0.003. So 0.003. And this is now to be equal to, so what is to be the ratio of the similar triangle that is to be bigger? So this triangle here. So itong malaking triangle na yan, we would be getting its slope also. So for the value here, so which, if this is to be C, this is now to be D. Because this is now to be its, the height of the triangle. So this is to be D. And for this part, or for the denominator side, we should be getting the total here. So once again, we would be comparing the smaller triangle. So this is to be the smaller triangle, and that is to be C divided by 0.003. And we would be comparing it with this very big triangle, whereas the horizontal dimension here would be strain U equal to 0.003 plus, so what is to be this dimension? So this dimension is to be your strain for your steel. And, well, so basically I would just be writing it first. So strain of steel plus 0.003. So that is to be the case here. Okay, so by the way, I think it is better if I would be explaining it this way. So for this first equation, that is to be this triangle here. So this triangle. So rise over run. So the rise of it, so its height is to be C, and its horizontal or its run is to be 0.003, which is to be this. So 0.003. And as for this equation here, it is now to be the bigger triangle. So it would be this, this, and this. So once again, similar triangles, ratio and proportion. So for the upper part, that is to be the rise or the depth of it. So from this point up until this point, or D. So that is to be D. And as for this dimension here, that is basically strain U plus strain S or strain steel. Or that is basically, that basically comprises of all of this. So ES plus EU, strain S plus strain U. And strain U is once again 0.003. Thus, this equation. Okay, so I will be erasing all of this first for you to understand it better. Okay, but what about for your strain S? So from your mechanics of deformable bodies or your strength of materials, so strain S or the strain of the steel is basically equal to the strength of the steel or the stress of the steel. So stress divided by modulus of elasticity. So memorize this one, guys. And for the modulus of elasticity, guys, this is for steel. Take note, guys. So for steel, this is to be a constant one. So this is to be 200,000 megapascals. So there. So with such, we can say that your strain S is now to be equal to Fs divided by 200,000 megapascal. So if we would be substituting this to this value of or strain S, this is now to be equal to, so C divided by 0.003 is now to be equal to D divided by Fs divided by 200,000 plus 0.003. So take note of this equation, guys. So this is now to be our equation. And if we would be solving for the value of C, so C cross multiplying, this is now to be equal to D times 0.003 divided by Fs divided by 200,000 plus 0.003. So we can actually simplify this one by getting the least common denominator of this. So basically, basic math. So basic math, simplify this equation, and it is to be equal to 600D divided by 600 plus Fs. So basically, guys, just memorize this. Both of these values here, so this value and this value is to be equal. So once again, take note of this formula. So you can copy it right now or you can take a screenshot. So C is to be equal to 600 D divided by 600 plus Fs. But the thing is, once again, we still do not know the value of our Fs. And if, for example, we already know the value of RC, so let's say that we already have the value for RC, so cross multiplying, so our Fs, so let's say Fs, this is now to be equal to, so cross multiplying, just solving for Fs, moving Fs to another side, this would now give you an equation of 600 times D minus C divided by C. So this is already the simplified equation. So take note of this once again. Okay, so moving forward, so there is actually another symbol or another value that is very important in reinforced concrete design. And that is to be your value rho. So when you say rho, so this is to be its Greek symbol, so rho. And rho in reinforced concrete design is basically the ratio of the steel, so your AS, divided by the total area of your concrete up until this point. So by the way, guys, even though that there are concrete underneath the steel rebar, so we are only considering this part. So we wouldn't be considering this area. So we are actually taking this concrete at the bottom part as concrete cover only. So anyway, once again, the value for your rho is basically the ratio of the area of the steel by the total area, total effective area of the concrete. And that is to be BW times D. So that is basically it. So BW times D, or this area. So once again, that is to be the ratio of the area of the steel at the tension side divided by the total area. So basic. So this one. So okay, I will be deriving another equation that will serve useful in our analysis. So if we would be getting once again this train diagram, so I will be copying once again. So apologies once again for my very unorganized solution. So for example, once again, that I will just be copying this train diagram, this stress diagram. So guys, just a reminder that this is much more, so this diagram right here is much more important than its formula. So if you cannot memorize the formula, it is okay, because using this diagram you can derive it. So this is much more easier to memorize than the formula itself. So once again, you can you can derive all of the necessary formulas if you know this diagram. So an example is that, for example, so once again, that since this diagram is into be a static condition, we can say that the summation of forces horizontal is to be equal to 0. So that is from your statics of rigid bodies. And if the summation of forces horizontal is equal to 0, we can conclude that the value of your compression is to be equal to the value of your tension. So that is to be C is equal to T. And if we would be substituting known values here, so for your C, if you can remember a while ago that this is now to be equal to 0.85 FC prime A times BW. So this is for your C. And for your tension, that is to be equal to, so equal to, so T is once again equal to AS times FS, or the area of the steel times the stress of the steel. So basic. And once again, your A, or the value of your A, is to be equal to betas of 1 times c. So remember this. And from the previous derivation, your value for your c is now to be equal to, so going back here, that is to be equal to 600, I'm sorry, that is to be equal to 600d divided by 600 plus fs. So 600d divided by 600 plus fs. So substituting both of these equations to this particular equation. So let's say that this is to be equation number 1, equation number 2, and equation number 3. So substituting 2 in 3 to arrive at an equation 4, and substituting equation 4 in equation number 1, this is now to be equal to, so 0.85 fc prime. So what is to be the value of a? That is to be betas of 1c. So betas of 1, so beta 1 times c. And what is c? That is to be 600d divided by 600 plus fs. Okay, there. Times bw. So times bw. So this is now to be equal to as times fs. So take note that the value for your as using the value of your rho is to be bw times bwd times rho. So cross multiplying, solving for as. So as is now to be equal to rho times bwd. So if we would be using this equation and we would be substituting it here, so this is now to be equal to rho times bwd. So bwd times fs. Okay, and using this equation once again for the value of your rho, so cross multiplying, so your rho is now to be equal to 0.85 fc prime times betas of 1 times 600d over 600 plus fs times bw, and you will now be dividing this by, so divided by bwdfs, so bwdfs, so canceling the terms that needs to be cancelled, so bw would cancel out and your d would cancel out. So with such, guys, so our rho here now is now to be equal to 0.85 times f prime c or fc prime times betas of 1 times 600 over 600 plus fs over fs. It would be much easier if you would be memorizing it this way. So once again, all of these are just the derivation part. And basically, this is to be the much more important thing here. You can actually solve for the value of rho if you know all of these parameters already. So it is either that you will be memorizing the formulas or just know this principle so you can derive it by yourself. Okay, but actually we can rewrite this equation right here in terms of stress. So I mean strain, I should say. So for example, that is to be your strain. So let's say that that is to be the strain that we have derived. You can actually rewrite this as strain U divided by strain U plus strain S. So if you can remember earlier that this equation came from this, it's just that your strain S, so your strain S is to be equal to Fs divided by 200,000, and that your strain U is to be equal to 0.003. So they are basically the same. But if you see this in books instead of this one, that is basically, well, I mean, they are basically the same. I have just simplified it here. Okay, so we still have a catch here. So after how many minutes of the video and after how many formulas that we have derived, we still do not know how to solve for the value of Fs. So once again, if we would be going back to our main equation, so once again, for our nominal moment, that is basically ASFS times D minus A over 2 or 0.85 FC prime ABW times D minus A over 2. So once again, we cannot solve for this moment if we do not know what the value of Fs is. And we still also cannot solve for this moment because the value of your A is to be dependent upon the value of your Fs. So once again, in Tagalog, di pa natin masasolve kasi di pa natin alam yung value ng Fs. Okay, so here in the analysis of reinforced concrete, there is a thing which we call balanced condition. So when we say balanced condition, so I will just be writing it here. So when we say balanced condition, so this is to be the condition wherein your Fs is to be exactly equal to Fy. So this is to be for your balanced condition. So for pretend that in this particular equation, so let's say that in this particular equation, so let's say that this is to be the particular equation. If we are to substitute Fs as Fy, so I will now be deleting this. So this is now to be equal to Fy. This is now what you would be calling your C balanced. So C balanced. And let's say in this particular equation, the latest equation that we have derived, so let's say this one. So if I would be placing them here, so if once again, if I would be substituting the value of Fy to the value of Fs, this is now to be equal to, so for a while, so I will be erasing this, and I will be also erasing this, and replace it with Fy. So Fy and Fy. This is now what you would be calling your balanced raw balanced. So once again, this is now to be equal to your raw balanced. And if you can remember earlier that when we say raw, so take note, raw is to be equal to the ratio of the area of the steel divided by BWD. So solving for AS, so AS is now to be equal to raw BWD. However, if we would be using raw balance, so for example, raw balanced times BWD, the answer here would now be equal to AS balanced. So AS bal. So what are to be the implications of this? So this condition is to be the condition, once again, wherein your Fs is to be equal to Fy. So what is to be the importance of this once again? So in reinforced concrete design, we have three controls. So we have our tension controlled. So I will just be writing them here. So we have our tension controlled. We also have our compression controlled. And in NSCP 2015, there is to be what you would be calling our transition. So for your tension controlled, so guys, take note, they are all controls. So tension controlled. So for your tension control, this is otherwise known as under reinforced. So under reinforced. And for your compression control, this is otherwise known as over reinforced. By the way, before I proceed, so for your tension controlled, it is indicated here that your strain T, so just memorize this guys, so strain T, or this is to be the strain of the outermost steel rebars, this should be greater than or equal to 0.005. So take note of these conditions. And your C here is now to be less than or equal to 0.375 times dt. And your rho is to be less than or equal to a rho balanced. So if you can remember, we know how to solve for your row balanced. So if the row of the actual member is to be less than your row balanced, it means that it is to be under reinforced or it is to be tension controlled. So if your row is now to be greater than your row balanced, it is now to be compression controlled. So once again, if your row is to be greater than your row balanced, it is now to be compression controlled because the implication here is that once again, your row is to be equal to AS divided by BD. So the greater your row, it means that the greater your area of steel is. So pag mas madami tayong bakal, mas mataas yung row. And kapag lumagpas tayo sa row balanced, ibig sabihin over-reinforced na tayo. Pag mas mababa naman tayo sa row balance, it is now to be under-reinforced. And in here guys, so for your under-reinforced, your Fs is to be greater than or equal to Fy. So take note of this. And for your, I think it is better if I would be drawing it in blue. So once again, your Fs is to be greater than or equal to your Fy. And for your compression control, your Fs is to be less than your Fy. Okay, and here guys, we can say in compression control that so strain T, it is to be less than or equal to strain Y. We can say that your strain T, this is now to be equal to your strain EY once again is to be equal to Fy divided by E. Or that is to be equal to, so once again, Fy divided by 200,000. So just take note of this guys. Okay, so what this implies is that dapat daw yung strain sa outermost fiber or the outermost steel does not reach the strain of its limit. So in other words, the most critical rebar should not exceed the strain of the limit. So it would be as simple as that. Moving forward. So the common misconception here, so when you say under-reinforced, syempre kulang sa bakal yan. When you say over-reinforced, sobra naman sa bakal. So one common misconception of people is that when we say that a member is over-reinforced, they say that it is to be much safer as compared to our tension controlled. So in Tagalog, ang common misconception natin is that kapag sinabi nating over-reinforced, mas matibay yan kaysa under-reinforced. But the truth is, it is not. Because if your member is to be tension controlled, you are designing it in a way that if your member fails, the steel would now be the one failing. And the method of failure for your steel is to be a much more ductile failure. And pag ductile kasi, mas mabagal siya nag-fail. So with that, guys, so if it is to be, if its failure is to be much slower, the concrete will slowly crack first. So for example, that there are to be earthquakes or there are to be failures, you would see that the structural members would slowly crack. So magka-crack muna siya. And by that, it will be giving you time to go out of the building or say your prayers. Basta magkakaroon ka ng time. So that is for your under-reinforced. But for your compression controlled or over-reinforced, so this one right here, the failure is to be much more abrupt. Or let's say it will be a brittle failure. So brittle failure yan. So if, once again, your member is to be compression controlled, that is, mas mabilis masira yung building. So without warning, it would fail. So once again, for your tension controlled, you would still be having your warnings. So there will be cracks first and it will slowly fail. And as for your compression controlled, without warning, babagsak at babagsak na lang yan. So I will be explaining to you via computations very soon why compression controlled is not advisable and tension controlled is to be the much better design parameter. Okay, so going back guys, so as you can see here, Fs is now to be greater than or equal to Fy. So this is to be our case here. And for your rho guys, so rho is to be less than or equal to rho balance. So you can actually compute for your rho already. So once again, your rho for the nth time, this is not to be equal to AS times B WD. So in the analysis part, so when we say analysis, alam natin yung section natin. So we already know the section and we are just solving for its MN. And actually, your AS is already given and your BWD is already given. So solve for it and compare it with the value of your raw balanced. And if it is to be greater, or if the value of your raw is to be greater, you would now be using FS be equal to FY. So yun. So with such, gagamitin nyo ngayon, Fs is to be equal to Fy. So if you are now confused, sabi dito, Fs is greater than or equal to Fy. So why is it the case that if it is to be this case, Fs is now to be equal to Fy? It is because that for the strength of your steel members or your steel rebars, Fy is to be the maximum stress. So Fy is basically equal to Fs max. So even though that you will be solving for Fs higher than your Fy, well, basically guys, hindi naman siya tataas kasi nga yung strength lang ng bakal mo is Fy lang. Hindi na siya tataas. So once again, if you would be solving for an Fs greater than Fy, you will now be assuming that your Fs is now to be equal to Fy. So for example guys, let's say that your grade, so the grade of your steel is to be grade 420. So when you say grade 420, by the way guys, this is to be a new grade from NSCP. So by the way, so grade 420, for example, that your grade is to be 420. So this is to be equal to, or Fy is now to be equal to 420 megapascal. So for example, that the Fs that you have solved is to be equal to 270. It means that it is to be less than Fy. So you would be using this kasi nga kaya naman ng bakal nyo kasi 270. The thing is, if Fs is to be less than Fy, it means that this is to be compression controlled. Okay, and for another example, once again, your Fy is to be 420 megapascal. And let's say your Fs, the Fs that you have solved is, let's say, 1,500 megapascal. And in this case, guys, your Fs is to be greater than your Fy. So, ulitin ko lang, ito lang yung capacity ng bakal nyo, pero yung nasolve mo ganito. So, with that, guys, you will be solving in your analysis, Fs is to be equal to Fy, since it is to be tension controlled. So, there, guys. So I will be explaining to you very soon or in the next video on how we would be making use of this using an example. Okay, so there. So what about for our transition controlled? So in our transition controlled, guys, so I will just be copying in a next slide kasi wala na tayong space, so we do not have any space any longer. So for our transition controlled, it is in here that your strain T. So once again, in this part, your strain T should be greater than or equal to 0.005. And in here, your strain T should be less than or equal to strain Y. So, yung nasa gitna nila, that is basically your transition zone. Or in other words, your strain T should be less than 0.005 and it should be greater than or equal to strain Y. So if this is to be the condition, you can also use this predetermined condition, no? So pwede din 3 over 8 times dt. Then this should be less than C. This should be less than 600 divided by 600 plus Fs times dt. So this is another condition or a predetermined condition. But if you have already solved for this, there's no use of solving for this because basically this equation is basically this equation that was derived. So gumamit lang siya ng ibang formula pero basically parehas yung dalawa. So anyway, so that is for the transition controlled. So the difference between your transition controlled, your compression controlled, and your tension controlled are to be the value of your phi. So for the value of your phi, guys, so where is that phi? So this is to be the value for our phi. Okay, so if you can remember earlier that for our design strength, that is to be given by the equation phi mn. And as for the value of mn, this can be written as, so as fs times d minus a over 2, or mn is now to be equal to a, oops, sorry, 0.85 fc prime ab times, abw times d minus a over 2. So once again, this is to be dependent upon your, the number of steel or your steel ratio. Anyway, so this is to be it. And so we already know how to determine mn. But what about for phi? So for your phi, we will be using this diagram. So it may either be 0.65, 0.7, 0.90, or any value in between both of them. So this is for your compression control, this is for your transition control, and this is for your tension control. So as you can see, this is for your tension control. So the phi that you will be using for your tension control is to be 0.90. And for your compression controlled, the phi that you will be using is to be either be 0.65 or 0.7. So as you can see, we have a spiral here and, well, others here. So ano ba yung spiral and what is to be the others? So for your spiral reinforcement, it would be like this. So as you can see, they are all to be connected. So this is for your beams. So in actuality, I have not yet seen a setup like this. Nakakita lang ako ng ganitong setup on Google Image. And for your columns, this is to be for your spiral reinforcement. So once again, if you would be using spiral reinforcement and it is to be compression controlled, you would be using 0.7 as your, let's say, as your reduction factor phi. So once again, this is to be for your spiral reinforcement, and this is for the others, or this lateral tie reinforcement. And as for this, so ayun lang siya. Okay, so once again, if you are in the compression controlled, your reduction factor is to be 0.65. And if you are tension controlled, if the structure is tension controlled, you will be using 0.9. And at the transition zone, you will now be using ratio in proportion. So it is either you can use this or the equation that I have shown you a while ago. Ay, wala pa pala akong pinakita. Ito pala. Oh, by the way, wala pa pala akong pinakita. So basically, you would just be making use, you would just be making use of this particular equation, or just, well, ratio in proportion from 0.65 up until 0.9. So similar triangles and whatsoever. Basta ratio in proportion. So once again, in this video, I will just be showing you the idea behind the design, or the analysis part, I should say. And for the succeeding videos, I will be showing you an example on how we would be making use of all of them. Oh, by the way, guys, before ending, there is also a shortcut in solving for the value of our mn. So by the way, guys, if you can remember, your mn is to be equal to 0.85 fc prime abw times d minus a over 2. So this is one equation. And another equation for your mn is to be equal to as fy times d minus a over 2. So once again, this is already predetermined. I have already derived this earlier. So another shortcut, so mn, can be solved by using the equation rho b d squared fy times 1 minus 0.59 rho fy over fc. So you can once again actually solve for this equation using the strain diagram. So yung stress diagram, I should say. So using this particular stress diagram, the one on your right. So if you would be substituting the value of your rho and others, so if you would be substituting the value of your rho and, well, other parameters, or let's say your value of your as, then basically you would be arriving at this particular equation. But take note, guys, that this formula right here is only used for rectangular sections. So this section, this formula cannot be used if your section is trapezoidal, if it is to be heart shape, or whatever section it is. So by the way, if you have already solved for it using this equation, if you have already solved it for this equation, then there is no need to solve for this too. If you have already solved for it using this equation, there is no need to solve for this too. And truth be told, guys, me myself, I don't memorize these equations. So sa totoo lang, hindi ko memorize itong mga equation na to. It's just that I know the relations of it using this stress diagram. So, well, basically that is to be it for this video lecture. And if there are questions, feel free to message me. So there.